In section 5.2, we're going to look at using perpendicular bisectors, both in general and also within triangles. So first, recall, you know what both of these words mean. You know what it means to be perpendicular. You also know what it means to be a bisector. So now we're just going to combine both of those ideas. So a perpendicular bisector is a segment, a ray, a line, or a plane that is perpendicular to a segment at its midpoint. So based on the diagram at the right here, if I wanted to mark that as being the perpendicular bisector, I first have to show you it's perpendicular, and then I also have to show you that it bisects. In other words, it cuts it in half. So there's your perpendicular bisector. Okay. One term that we're going to use quite often throughout this chapter is the term equidistant, and it probably means exactly what you think it means, and that is it's equidistant. A point is equidistant from two figures if the point is the same distance from each figure. So equidistant just means the same distance. So the perpendicular bisector theorem simply says if a point lies on the perpendicular bisector, then it is equidistant, it's the same distance, away from the endpoints of the segment. So for example here, if we know that point C lies on the perpendicular bisector, line CP, then that means the length of CA has to be the same as the length of CB. Okay, and that's what the perpendicular bisector theorem says. The converse to that says if you know that a point is equidistant from the endpoints of a segment, then it must lie on the perpendicular bisector. So in this diagram, we know they tell us that DA and DB are the same length, therefore we know it must lie on the perpendicular bisector. And that's the converse. Okay, so AC is the perpendicular bisector of BD, solve for AD. Well, as soon as you know that this is the perpendicular bisector, you know this, you know that, but the real thing you need to identify here is that A is equidistant from the two endpoints. And so 7x minus 6 has to be the same as 4x. So now when I solve this, I just subtract 7x from both sides. So I get negative 6 equals negative 3x, divide both sides by negative 3. I find that x is 2. The question says solve for AD, so I plug this guy back in here. 4 times 2 is 8. Example 2 says in the diagram KN is the perpendicular bisector of JL. What segment lengths in the diagram are equal? Okay, well, based on the fact that we know point K lies on the perpendicular bisector, we know that JK has to be congruent to LK. All right. We also know that N's the bisector, so we know that JN and LN are also congruent. And based on the fact that this is 13 and that's 13, we can say that JM is congruent to LM. So that's all we know in the diagram. We know all those segments are congruent. Now part B says, is M on KN? Well, KN's the perpendicular bisector, and since M is equidistant from L and J, that means, yes, it must lie on the perpendicular bisector by the converse of the perpendicular bisector theorem. Example 3, we know KM is the perpendicular bisector. Find JK. So again, same idea. We know that these two things must be equal. So 7x has to equal 3x plus 16. I'm going to subtract my 3x from both sides. So I get 4x equals 16, which says that x equals 4. Now that I'm looking at this, I actually got ahead of myself here. I'm going to use this information actually in part B to find the length of ML here. So I know that x is 4, so when I plug 4 in there, you get 3 times 4, which is 12, plus 16. 12 and 16 makes 28 for ML. Go ahead and erase this and get back to square one and do what I should have done in the first place. So now the part A, originally, what I should have done in the first place is, it says find JK, so find this length. Well, again, they tell you that this is the perpendicular bisector, so you know these two lengths have to be the same. So 2y plus 9 has to equal 5y. So we're just going to subtract our 2y from both sides. So 9 equals 3y. So y equals 3. Plug that guy in here. 2 times 3 is 6 plus 9 is 15. So we're just using the perpendicular bisector theorem. Okay, same idea here. I'm going to let you guys work through this one on your own. If you want to find WZ, okay, again, you have to identify equidistant, perpendicular bisector, etc. Okay, try that one on your own there. So again, pretty quick video. We will talk more about this tomorrow in class, but long story short, that's what we're talking about when we talk about perpendicular bisector theorem.